So, after looking at partial derivatives and after looking at partial second derivatives, the time has come to actually find tangent planes. Similar to tangent lines, they will touch the curve at one spot, and at that spot have the exact same slope as the three-dimensional curve does. Every tangent plane is really just 3 steps. They're very easy. I'm going to go through one example, then I'll show you the graph, and hopefully you're very impressed at how it all lines up. What we're not going to see today and would come in multivariable is how you find horizontal tangent planes, which I think you could probably reason your way to, and how we know if those planes represent maximums or minimums. So we'll get to that, or you'll get to that probably next year, but for now, let's just make this tangent plane. So here are the 3 steps to making a tangent plane, or I guess the 3 things you need. Number 1, you need the quote-unquote point. I say quote-unquote because, of course, it's a little bit different in 3 dimensions, but that just means we're going to plug in -2 and 3 to our equation. So we got 2 times -2 squared plus 3 times 3. So 2 times 4 is 8 plus 3 times 3, so 8 plus 9 is 17. Okay. Step 2, we need our partial derivative with respect to x. Okay. So we treat x as the variable and y then is a constant, so that just means our derivative is 4x. And now we evaluate that at the point -2, 3. Well, of course, there is no y, so just plugging -2 in, we get -8. Okay, 3rd step, we need the partial derivative of f with respect to y. Again, treating y as a variable and x as a constant, our derivative is just 3. We would evaluate that at -2 and 3, but of course, there's no place to plug anything in, so it'll just be 3. So now, similar to when we did tangent lines, we have our point, minus, because it's minus, subtract 8, the x slope, and then x minus -2, which of course would be x plus 2. Maybe I should keep the signs as pluses for now. Plus 3, the y slope, y minus the y coordinate. So 17 minus 8 times x plus 2 plus 3 times y minus 3, and this is our tangent plane. Okay, so here's what you would see of those 2 graphs if you actually graph them on your on the computer or on an app. The app doesn't actually record straight onto onto this program, so I had to actually film it. But this is the graph. This is the original curve. And of course, this is the tangent plane. What I just wanted to show you here is the view of it. You can see very similar looking to a tangent line in this case, where we've got our curve, and at the point of tangency, we have that one exact spot where it touches. Kind of looks cool when you look at it this way. You can see that one spot kind of shaded where they share that instantaneous point. But that is what a tangent plane looks like.